Hello, my name is Josie, and thank you for tuning in to my presentation on meander bend cutoffs and how their persistent, non-local effects induce more cutoffs. The process of bend cutoff regulates the sinuosity and evolution of meandering rivers and their deposits. Predicting when and where cutoffs occur is an important goal for predicting the long-term behavior of meandering rivers. An important new insight into understanding cutoffs, published recently, shows that cutoffs have significant non-local effects. When a bend cuts off, it removes a certain length of the river and steepens bed slope, which in turn increases stream power and migration rate both upstream and downstream of that cutoff. This increased migration rate is what we refer to as non-local effects. In the spatial extent of that accelerated migration scales with the length a cutoff removes, as shown in the graph on the lower right. Yet to be determined, however, is how long these non-local effects tend to last, and if they are strong enough to accelerate the formation of more cutoffs nearby. Could the persistence of non-local effects dictate the spacing and timing of cutoffs in the long term? If cutoffs can non-locally increase the migration rate upstream and downstream, then that increased migration rate can conceivably lead to more cutoffs. Our hypothesis is that non-local effects accelerate the formation of cutoffs in nearby bends, leading to clustering in space and time. It has been questioned before whether cutoffs do cluster, and if clusters represent a chaotic system reaching a supercritical state. Perhaps this supercritical state of rapid movement is induced by cutoff non-local effects. We set out to test this hypothesis by tracking non-local effects through time on 9 sample rivers, using RivMap and MATLAB to extract centerlines from global surface water dataset channel masks and measuring migration rates. Additionally, we use results from the remote sensing analyses to implement non-local effects into a numerical model and simulate clustering. First, I will explain how we track non-local effects on a group of tributaries in the Amazon River Basin. The map on the left shows the locations of all samples run through our non-local effect tracking methods. To explain these methods, I'll focus on one sample, Reach C, a reach in Bolivia about 60 kilometers long, which drains into the Mamoré. Between 1984 and 2019, this channel experienced 7 cutoffs, circled in the red dashed lines. On the bottom right, we have yearly channel masks from the global surface water dataset overlain and colored by year. All of the migration measurements begin with channel masks like these, over which yearly centerlines are drawn, and then migration areas between years, and consequentially rates are derived. Let's zoom in on the red circle farthest to the right for a visualization of why this sample looks clustered. Visually, cutoffs appear to be clustered. An example of this avalanching behavior can be witnessed here. Accelerated migration following cutoffs may be the agent responsible for this unraveling, produced by the river rapidly constricting its sinuosity. But we need more evidence to back this up, as clusters have only been identified on single rivers. Next, I'll demonstrate how we detect non-local effects for this potential cluster. To isolate non-local effects, we subdivide the length of the river into multiple regions of interest, foregrounds and the background. These regions act to separate cutoff affected from cutoff unaffected bends, as to measure a base level of movement or control rate, above which we can detect acceleration. Foregrounds are the areas of the reach affected by each individual cutoff, determined by cutoff length removal. These regions can also be thought of as the shadows of non-local effects. Each cutoff on Reach C has a corresponding foreground, pictured in the smaller images to the upper right. We also define the background, or the areas unaffected by cutoff non-local effects and outside of every foreground. We compare lateral migration rates in each foreground with the background, to see if we can pick up non-local effects as a signal propagating through specific parts of the system at specific times. Through this comparison, we further characterize non-local effects by determining their temporal fingerprint and magnitude. For the first foreground of a potential cluster, we plot a time series of migration rates measured in the background, shown in orange, and in this specific foreground, shown in blue. Measurements are averaged over 2 years, beginning in 1984 and ending in 2018. The cutoff associated with this foreground is highlighted by a green line. We also compare rates by plotting the foreground rate as a percent change from the background rate. You can see that the background and the foreground are migrating at roughly the same pace before the cutoff in 1987, but then the foreground moves much faster than the background immediately following the event. We can track this elevated migration rate through time and note that the magnitude of this accelerated migration decays until it settles back down to the background rate. Before the acceleration has totally decayed, another cutoff occurs, and more after that, highlighted by red vertical lines. In this example, we determine that non-local effects last for at least 10 years after cutoff occurrence. Here are the same plots of migration and percent change on the left, and an image of the foreground on which these measurements were made to the right. Building upon this method, we add a row for every subsequent cutoff, but measure the foreground rate in the new cutoff's foreground. In this row, plots report migration rates in the same background, but this time foreground rates are measured in this next cutoff's foreground, occurring in 2004 and pictured to the right. Again, the foreground is migrating at roughly the same or slower than the background before the cutoff, and non-local effects are detected for 6 years following the event, leading up to a third cutoff in 2012. We add another row for the cutoff in 2012, whose non-local effects again lead into another cutoff, but this time it occurs only 2 years later. It should be noted that these cutoffs have similar migration plots. This makes sense, since their foregrounds are roughly the same. Once all cutoffs in a potential cluster are plotted, we can highlight each event's non-local effects. Then we can track these non-local effects as a wave moving through the system. We see a pattern here of accelerated migration introduced by the cutoffs, persisting for years after they occur and leading up to the occurrence of more cutoffs. This behavior leads us to believe that non-local effects might relate these events to each other and prove that they are not occurring near each other in space and time randomly. We were able to perform this methodology for tracking non-local effects on 9 sample reaches, 8 of which had significant non-local effects detected. We tried on upwards of 20, but many had to be let go from our samples due to gaps in channel mask imagery or lack of background area. In summation, we found overlapping non-local effects with subsequent cutoffs in 5 out of 9 samples, with some increasing background rate in their foreground by 5 times, and detectable non-local effects for up to 10 years after occurrence. This breadth and magnitude of non-local effects adds to the significance of cutoff impact on neighboring bends, beyond what we already know about their spatial extent. Moving on, we want to know if this new information on non-local effects can help us determine the cause of cutoff clustering. We take key findings of the temporal signature dissipating by 10 years, the spatial signature being detectable for the 1.19 times the length removed by that cutoff, and an average magnitude of 3 times the background rate, and combine these with the knowledge that river meandering is significantly driven by centerline curvature. Now we have enough information to implement non-local effects into a numerical model of river meandering. We opt to use MeanderPy, an existing centerline migration model based on curvature, then add in a non-local effect every time a cutoff occurs. As meander pi determines how far to move each centerline node in a time step, it requires a nominal migration rate. The nominal rate is then scaled by local and weighted upstream curvatures. To account for non-local effects, we add a normally distributed bump centered at the upstream node at which a cutoff occurs and the time step following that cutoff. Every bump has a standard deviation so that its majority falls within the 1.19 times cutoff length removal, both upstream and downstream, and decays with each time step, so that the entire bump is gone by 10 years of model time. The amplitude of this bump is set to 4 times the background rate, so that the mean migration rate over the area of interest is close to what we measured in our remote sensing analyses, 3 times the background rate. Moving forward, we plan on testing alternative shapes, but this provides a reasonable estimate of non-local effects based on our remote sensing analyses. The next slide shows an animation of a migrating synthetic centerline with corresponding decaying bumps and the nominal migration rate along its centerline. As the channel migrates and adds length to its centerline, it eventually cuts off and removes length. Every cutoff introduces a bump as shown in the previous slide. However, this example has faster rates to help visualize how they are implemented. Bumps overlap and are expanded or contracted accordingly with centerline migration. After generating a synthetic centerline of roughly 100 bends with a geometry like our samples, we ran the original model without implementing non-local effects, keeping track of each cutoff's occurrence in relative distance downstream on the y-axis and in model time on the x-axis. We opt to plot cutoff distribution in 2-dimensional space-time instead of 3-dimensional x location, y location, and time, since the relative distance here is along the centerline, which changes length constantly. For this, reach migrating at a relatively fast background rate of 5 meters per year with no non-local effects introduced by the cutoffs. 535 cutoffs occur, which produce this distribution. On the right, in the same space of distance downstream on the y-axis and year of occurrence on the x-axis, is the resulting distribution when we run our model with non-local effects on the exact same setup as the initial run. First, we can note that considering non-local effects in the way we model them increases the number of cutoffs this reach experiences. Beyond that, there are some possible areas which cutoffs might look like they are distributed differently than without non-local effects, such as more regular spacing here and more grouped areas here, but it's certainly not strong enough to tell without statistical tests. These first results are not yet enough to make any conclusions, but we are currently working on implementing statistical tests to quantify spatial and temporal regularity, randomness, and clustering, as well as testing distributions produced by various channel geometries and different background migration rates. By further defining the accelerated migration produced by cutoffs, we have shown that cutoffs can cluster due to their non-local effects. First results from numerical modeling suggest that non-local effects, which are persistent through space and time, could contribute to cutoff clustering. Next, we will impose statistical tests on these cutoff distributions by comparing them to complete spatial and temporal randomness. We also will further explore the shape of non-local effects as it is implemented with meander pi. Our findings do imply that non-local effects are the agent of cutoff clustering or avalanching, and that clusters are not just a way that meandering rivers respond to external forces, but can be produced autogenically. This has implications not only for meandering theory, but for the interpretation or modeling of stratigraphy and prediction of reach-specific susceptibility to clustering, which could be helpful for river management.